Good morning. In this lab video, we will present on the second experiment, which is center of pressure. The objective of this experiment is to determine the center of pressure and the hydrostatic force due to water acting on a partially or fully submerged vertical surface. Hydrostatic forces are the resultant force caused by the pressure loading on a liquid acting on a partially or fully submerged surface. The center of pressure is a point where the immersed surface at which the resultant hydrostatic pressure force acts. In this experiment, when a quadrant is immersed by adding water to the tank, the hydrostatic force applied to the vertical surface on the quadrant can be determined by considering the following, which is the first one, the hydrostatic force at any point of the curved surface is resolved through the pivot point, as we can see in this picture, so there is no torque to affect the equilibrium. And the second one will be the force on the side of the quadrant is horizontal and cancel each other on an equal and opposite side, so there's no force acting. Whereas the hydrostatic force on the vertical submerged surface is counteracted by the balance weight, the resultant hydrostatic force on the face can therefore be calculated from the value of the balance weight and the depth of the water. Then the system is in equilibrium if the moment generated about the pivot point by the hydrostatic force and added weight are equal to the equation as shown in this slide.
This one is D and the last one is L. The first step is data for D, B, L, and H was recorded. This one is B. The apparatus was adjusted until the bubble at the center. The quadrant was wiped using a wet coat to avoid surface tension and bubble formation. The quadrant was placed into the aquarium and checked to be. The weight hanger was placed at the end of the balance arm. The counterbalance was adjusted until the balance arm was perpendicular to the level indicated. The drain valve was connected with a pipe and placed at the dish and fully closed. Slowly added into the tank from the wall of the container until the balance arm was perpendicular to the level indicated. Loads was added to the weight hanger. Water was steps was repeated by adding 50 grams of weight until the tank is almost full with water. The reading of each weight is recorded. The previous step results were taken by removing the weight by 50. The drain valve was slowly opened to release the water until the balance arm was perpendicular to the level indicated. Extra
Width of the quadrant face B was set at 0.075 meters, the height of the quadrant face D at 0.1 meters, the length of the balance arm L at 0.28 meters, and the distance from the base of the quadrant to the pivot H at 0.196 m. This experiment, we measure the hydrostatic forces, depth, and type of submersion for different masses. The table below summarizes the experimental and theoretical values, as well as calculated error percentage for both partially submerged and fully submerged vertical surfaces. We observed that as the mass increased, so did the hydrostatic force exerted by the water. We measured depths and calculate the depth of the center of pressure, comparing it to the theoretical value to determine the percentage error. The data displayed in the above table demonstrate the hydrostatic forces, depth of center of pressure, and type of submersion for each mass. Let us take a look on the calculation for partially submerged vertical surface. To calculate the hydrostatic force for a partially submerged vertical surface, we will use the formula below, which is F equals to 1/2 rho g BD power of 2. Considering rho equals to 1000 kg per meter cube and g equals to 9.81 meter per second square as constant and b equals to 0.075 meter as the width of the quadrant face, we substitute the depth of the water from the base of the quadrant D into the formula to obtain the hydrostatic force. Additionally, to determine the experimental depth of the center of pressure for a partially submerged vertical surface, we employed the formula H equals to mgL/F. Here we will utilize the mass of the load m, acceleration due to gravity g, length of the balance arm L, and the previously calculated hydrostatic force F. Moving on to fully submerged vertical surface, we utilize different calculation. The hydrostatic force for this case was determined by the formula F equals to rho g BD multiplied with the small d minus the capital D over 2. In this equation, we consider rho equals to 1000 kg per meter cube, g equals to 9.81 meter per second square, b equals to 0.075 meters, small d as the depth of the water from the base of the quadrant, and the capital D as the height of the quadrant's face. The experimental depth of the center of pressure for a fully submerged vertical surface was calculated using the formula H equals to ml over rho b capital D times small d minus capital D over 2. Here we substitute the value of rho b, capital D, L, and the small d into the equation along with the mass of the load m. The experiment focused on the depth of the center of pressure for a partially and fully submerged vertical surface. Through the calculation of the hydrostatic forces and experimental depth, we obtained the result that we will compare to the theoretical value, allowing us to assess the accuracy of our measurement. The table presented earlier summarized these findings.
Discussion consists of 5 parts, which the first one is to calculate the center of pressure for partially and fully submerged quadrant. For partially submerged quadrant, we will use the formula of capital H minus small d over 3, where the capital H is the distance from base of quadrant to pivot, small d is the depth of water from base of quadrant, and the value of H is equal to 0.196 meter. Applying to the equation, we will get the value of the theoretical depth of center of pressure for partially submerged quadrant equal to 0.1812 meter, 0.1748 meter, 0.1697 meter, and 0.1652 meter, and the value of D is equal to 0.0445 meter, 0.0635 meter, 0.079 meter, and 0.0925 meter. While for the fully submerged vertical surface, we will use the formula of capital D square over 12 plus small d minus capital D over 2 to the power of 2 over small d minus capital D over 2 plus capital H minus small d, where the capital H is the distance from the base of quadrant to pivot, small d is the depth of water from the base of quadrant, and the capital D is the height of the quadrant face, where the capital D is equal to 0.1 meter and capital H is equal to 0.196 meter. And the value of small d is equal to 0.1055 meter, 0.1185 meter, 0.133 meter, and 0.145 meter. We will get the theoretical depth of the center of pressure for the fully submerged vertical surface is equal to 0.1610 meter, 0.1582 meter, 0.156 meter, and 0.154 meter. The calculation is repeated by using the same formula for d equal to 0.158 meter. The second part of the discussion is the photograph, where they are illustrated in figure 7.1, which is graph of hydrostatic force versus the depth of immersion. Figure 7.2, the graph of experimental depth of center pressure versus depth of immersion. And figure 7.3, which is the graph of theoretical depth of center pressure versus depth of immersion. The third part is to discuss the variations of hydrostatic force with depth of immersion. From figure 7.1, it demonstrates clearly that hydrostatic force is directly proportional to immersion depth for both partially and fully submerged quadrants, since the graph shows a linear trend. To conclude, when the loads are applied, the quadrant becomes submerged. As the depth of immersion increases, the pressure exerted by the fluid increases. Consequently, the hydrostatic force on the submerged object increases. The second last part is to discuss on the relationship between the depth of center pressure and the depth of immersion. This relationship can be shown in figure 7.2 and 7.3 for both experimentally and theoretically. The depth of pressure center is shown in both graphs to be inversely related to the depth of immersion. The center pressure's depth decreases as immersion depth increases. As the depth of immersion increases, the center pressure also moves deeper into the fluid.
The fifth part of the discussion is to compare and explain the discrepancies between the experimental and theoretical result for the central pressure. The percentage error for different masses of the object is calculated as 4.02x7%, 5.9497%, 5.7749%, and 5.6295% for masses of 0.05, 0.1, 0.15 and 0.2 kg respectively. By observing the graph in figures 7.2 and 7.3, it is shown that the depth of the central pressure will decrease when the depth of immersion increases. This is mainly caused by the increase in the depth of centroid from the free surface, which causes the central pressure to move closer to the centroid. From the calculated data, it is observed that the experimental central of pressure has a higher percentage of error than the theoretical one. And this situation can be explained by several experimental errors occurring. The errors that might affect the accuracy of the experiment include parallax error, splattering of water droplets on top of the quadrant's surface, and the placement of the apparatus on an unbalanced table. Hence, in order to minimize these errors, certain preventive steps must be taken to minimize the corresponding errors during the experiment. In conclusion, this experiment proved that a fluid will exert force on a planar surface when it is enclosed behind the surface, and this force will be affected by the fluid's composition, level, and surface properties. The inaccuracy that is contributed by technicalities like weight, water volume, or impurities in the water tank is around 4 to 5% of the theoretical values. From the graph plotted, the hydrostatic force is said to be linear with the depth of immersion. And finally, errors can be minimized by running multiple tests and obtaining the average result to improve the accuracy of the experiment.